Okay, I think some folks are kind of running behind schedule. I know we're getting to the end of a very long conference, but I want to make sure we get started with our last plenary session today, and then we'll continue into the poster reception. So I want to just go ahead and introduce our first plenary speaker in this session, Tesary Lin, who's from Boston University. Really glad to have you, and take it away, Tesary.
Thank you. Awesome. So thank you for the organizers for inviting me. It's my great pleasure to be here, as always. And so during the fireside panel session, I'm also very excited to learn that actually in this room, there are a lot of people interested in understanding how much consumers value privacy. And this has been my research agenda for kind of the past 5 or 6 years or so. So the topic of the talk today, I'm going to talk about several of my kind of past and recent studies that try to understand the nature of consumers' privacy preferences and the some of the impact of common data collection practices using experiment as a tool. Okay. So I know that most of us in the room, you have been actively collecting and analyzing consumer data as your day job. But the practice of collecting and analyzing consumer data and the effort of collecting that actually goes way back, starting 1981, when the first membership program by American Advantage was launched. So we have begun, quite a long time, trying to understand, consumers via collecting their data. And of course, we've gone a long way. And nowadays, the practice of, trying to understand the consumers only become more prevalent because, well, the modern advertising needs consumer data, and also modern algorithms needs a lot of data to be able to be powered up. Okay, so now, sometimes, well, companies want to say, okay, I want to get as much of data as possible, but of course, well, not all of the consumers are willing to share the data with the companies. So sometimes you will also see that, well, the companies are trying to incentivize the consumers into sharing the data with them. Actually, in recent years in Europe, there are a lot of the publishers trying to give incentives to encourage data sharing. So what they set up is what they call as a pay or tracking model. Either you use my product for free with tracking, or alternatively, if you don't want me to, want the company to track you, you can alternatively just pay using a monthly subscription fee, and then you can buy back your privacy. So in this screenshot, this is a screenshot from Meta, back when they were trying to launch their own pay or tracking model, right? And you see that, well, the pay option, it says, well, you can pay $13 a month in order to get back your privacy. So now the question for every one of us in the room is that, well, is that the right price for data? Now, in order to understand this question, we definitely want to know how much do consumers value their privacy? And going back to the fireside panel session, when you're trying to develop an algorithm that tries to balance the utility from the algorithms, the accuracy of them, and the privacy, you also want to know how much weight consumers put to privacy. Now, this is a very difficult question to answer, for sure. And there are a few tricky points, which has all been touched upon in the previous discussions. Number one, there is something that we know as privacy paradox, which means that, well, the stated preferences for privacy and the review preferences are not completely aligned. So consumers can say 1,000 different things. Well, they can say, well, I value my privacy a lot, but if you look at their actual behavior, they may not look like they value privacy a lot. Okay, that's a number one conundrum. Number two, we also know that, well, what they do and also what they say, whether they value privacy, depend a lot on how you ask them. This is what we know as the context dependence of privacy preferences. And then, as a result, you see some of the common sentiments saying that, well, privacy preference is so hard to measure, we should just give up the measurement exercise altogether, and just forget that, well, pretend that it doesn't exist in the managerial and policy discussions. I don't want to do that. So what I'm going to do, I'm going to show you some of the studies that try to tackle some of these measurement challenges. First, what I'm going to do, I want to try to see how much actually do consumers value their data, and how do different consumers value their data differently. Now, for empirical researchers, it's useful and important to understand how different consumers value their data differently because, well, you want to know who are the consumers who self-select into sharing the data to the companies. That will manifest in the nature of the selection bias in your sample data. We know that selection bias could be could drive the quality of your decision a lot. So we want to understand the nature of the selection bias driven by heterogeneous privacy preferences. Later, I'm going to switch gears a bit. I'm going to look at the data collection practices. One common practice is what we call as choice architecture in economics and social science, which means that, well, you can design various types of interfaces to nudge consumers into sharing. So the first aspect that I'm going to talk about is that, well, how should we think about the role of choice architecture in affecting the selection bias in your sample? Second, I'm going to zoom back a little bit and look at the choice architecture effect and how do choice architecture affect different types of companies in general. And we want to ask the question, how does choice architecture affect websites competition for consumer data? Okay, so let's look at the first two questions. So the elephant in the room is really, well, can we really reliably measure consumers' privacy preferences? Let's go back again to 1981, but this time let's look at Gary Becker. So Gary Becker seems to have a theory for everything. And in this 4-page essay, he also has a theory about privacy preferences. And what he says is that, well, a person can value their privacy just because, well, they think of that as a taste. So they value privacy on its own right. That could be one motivation that people want to protect their data. Or they may also value their privacy because they are afraid that, well, revealing that private information will lead to negative economic and social consequences. In other words, we could really think about the value for privacy as consisting of two different components. One, you could think about it as an intrinsic component. So this is a taste for privacy. It does not attach to any concrete consequences for revealing private information. And the other is what I would call the instrumental component. So it will really vary depending on whether the data is used for targeted advertising, personalized recommendation, or used for AI training. Okay? So you could formalize it in mathematical terms, which I did in my paper. But what I want to draw your attention to is the fact that, well, thinking about the fact that, well, the consumer's privacy preferences actually have these two components, have implications on how we think about the measurement, and it has implications on how we think about selection bias. So number one, when we think about the fact that, well, privacy preferences have this instrumental component, it basically implies that, well, some of these context variations are actually systematic because it varies very systematically with the consequences of data sharing. So if you have a good model, you could actually capture the systematic variation, and it does not actually reflect decision noise. So this is one implication from the theory. And number two, when we think about the intrinsic preference, okay, so if consumers also value privacy by its own right, and if different consumers actually value privacy intrinsically to different degrees, that actually complicates selection bias a little bit, because now that you look at people who choose not to share the data, you would not really think that, okay, so these are definitely people who worry about the negative consequences of, well, sharing the data. So economists often have this simplified thinking that, well, these people who choose not to share data, they are definitely people who have something to hide. We do not want to make that simplified assumption here. So the actual selection pattern could be more complex than a simplistic assumption would imply. Okay, so that's the theory. We could put that into into the data. So let's see how it shows up. So in order to test that theory, I'm going to design an experiment that try to separate out the intrinsic and instrumental preference component and also try to quantify it in dollar terms. So now going back to the privacy paradox, to the extent that stated and review preferences disagree, we are going to heavily focus on the review preferences because that is something that directly affects the data sharing decision. So we're just going to focus on the review preference for now. In the experiment, let me highlight the key components. So the treatments, we are going to introduce variations in instrumental preference. Here, the instrumental preference would mean that, well, if you share the data, you would get a higher payoff if the company knows that you're high income and a potential buyer for their product. So that's the instrumental preference component in my study. In the control group, I'm going to shut that instrumental incentive off. So there is going to be that variation, and then I am also going to vary the price for data. So this is a take it or leave it offer. It basically means that, well, the consumers are going to compare the privacy cost and the benefit from sharing the data. So this is going to be a review preference measure. And then we also have the baseline survey components, and these are actually very useful for us. So first, we are going to measure the demographic composition from every participant. So the goal of that is really trying to back out the distribution of the participants. That allows us to get to a measure of, well, the distribution of the consumers even before we ask them, well, whether are you willing to share your demographic data with the company. So what we are going to do later is to compare the sample data with the population data and to get a sense of, well, what is the nature of the selection bias and how biased the the sample data really is. And then we also have a conjoint survey component. So for the people who are not familiar with the conjoint survey, so this is really a survey component that tries to measure how much do consumers value different attributes of a product and how do that compare with their price sensitivity. The usefulness of this component is that we can actually put that into a pricing exercise. So later, something that we are going to do is that, well, we are going to see how well we can predict consumers the optimal prices that we charge to the consumers based on the full data versus based on a selected sample. So that will allow us to get to a quote-unquote value of data and characterize, well, what is the impact of the selection bias on on the data value. Okay, so what do we find in this study? So first of all, we see evidence that, well, intrinsic preferences are highly heterogeneous. Now, these are the distribution of the intrinsic preferences across different demographic attributes, but you can really sum it up and see what is the distribution of privacy preferences for sharing a whole demographic profile with the company. So the mean preference is around $10, but if you look at the tail, so it usually have a long tail pattern, which is well replicated in subsequent studies. If you want to look at the 97% quantile, that amounts to around $30. So that means that, well, if the company wants to collect 97 percentile of the data from their consumers, they would need to pay $30 per customer. So here it's basically showing you the heterogeneity of the intrinsic preferences. In terms of the instrumental preference, so here, okay, so this version of the slides does not have the annotation, but here, what I show here, the bar is representing the distribution of the income profile. So the red represents the high-income customers, and the blue represents low-income customers. So there is the bar there that represents the ground truth, which is the distribution of the income in the population. And then you can also look at the distribution in the share data and how that varies with the instrumental incentive. So here, what you can see is an existence proof that, well, as the instrumental incentives scale up, you start to see more and more high-income people share the data, willing to share the data with the company. Now, if you shut down the instrumental incentive, the data that you have, they are both mostly consisting of low-income consumers. Lastly, we see evidence that, well, selection bias really distorts the pricing decision. So here, let's look at different types of exercises here. Okay, so you can look at the gray, gray line, which is the prices that you will get if you use the full data. So that is going to be our ground truth benchmark. Now, if you look at the blue, that would be your pricing inference if you have the sheer data and you do not apply any type of correction in your pricing algorithm. So you see that most of the time the prices are biased downwards. Why? Because most of your data consists of low-income consumers. Now, there is one trick that you can pull, a simple trick, which is that, well, okay, you can actually put the privacy choice indicator into your pricing model. So you can kind of put the indicator whether a consumer agrees to share the data with you. Okay, so what does that do? If you put that indicator into the pricing model, it debiases the inference in your in your pricing inference. So what you see in the orange there is that, well, kind of the prices kind of get more centered around the gray, which is, again, the ground truth. Interestingly, you don't see a lot of the variance reduction in your predicted prices. So adding the indicator is going to help you remove the bias in your in your inference. It doesn't remove the variance that much because a lot of the variance will rely on the actual granular information you learn from the actual data. Okay. So now, so this is basically kind of the first study. So let me shift gears a bit, and I'm going to kind of shift to the other side and look at the impact of a common practice in data collection. So this is the kind of example that I showed earlier on that shows you different types of data sharing consent banners. So you can see that while companies are really putting a lot of efforts in trying to convince consumers and nudge consumers into sharing data, and in doing so, they will use all kinds of user interfaces that maximize the possibility that the data is going to be collected. In the example at the top, what they do is that, well, they hide the reject all button, right? This is something that you can see. In the second example, in the app interface, they put the default as I am going to, they are going to put the default as, I'm going to use the product for free with tracking. So default and hiding the options are two very common choice architecture, which means that, well, these are user interface designs that nudge consumers into making an action desirable to the firm. So companies have been doing this. I know many of you guys are actively using experiments to optimize the choice architecture. And oftentimes, consent management platforms are also trying to offer the products that help the companies optimize. But oftentimes what we see is the following. Okay, so we are trying to optimize for the choice architecture for data collection. But the objective is usually trying to maximize the consent rate, which translates to the implication for data. It means that, well, we are optimizing for user volume, or the volume of the data being collected. So now the question for us is that, how should we think about the impact of this optimization practices for the bias in the data? Because, well, as empirical researchers, we know that, well, when we think about the quality of the data, we should really think about two dimensions. Volume is just one dimension. We should also think about how representative the data is. And it doesn't seem right to just optimize for the volume. So the question for us is really that, well, how does the current choice architecture optimization practice do in terms of, well, the impact on selection bias? So I'm going to show you a simple example to show how we think about the problem. I'm going to cast this problem in a supply-demand framework. So think about the consumers as the suppliers for data and the companies as the demand for data. So here you have this demand and supply framework, but you also see that, well, there are multiple supply curves. Why? Because the supply for data from the consumers is easily shifted by choice architecture. Now, imagine that, well, in the example here, you have the supply curve 1, which represents the case where a company does not engage in any type of optimization. So this is our benchmark. Alternatively, they can also try to optimize for maximizing volume. Now, the impact of that optimization is going to be shift out the whole supply curve. So the supply curve is going to be pushed out and pushed down. Okay, so how does it actually kind of like, impact this kind of data representation and data composition? We are going to look at the composition of the consumers who share. So here you see the two different colors that represent the low income and the high income consumers. So the low income consumers are in yellow and the high income are in blue. Everyone who agrees to share the data would be the people whose valuation for data are lower than the price point. So we are going to look at the interaction between supply and demand and see who are the people who actually agree to share. Now let's focus first on the kind of neutral. So here you see that, well, roughly speaking, 1/3 of the high-income consumers share the data, 2/3 of the low-income consumers share. So this, roughly speaking, is similar to kind of what you see across the population. However, if you start to look at kind of the composition of the consumers in the volume maximizing case, you see that, well, actually, in this case, most of the consumers who share the data are the low-income consumers, and the high-income consumers is a tiny fraction in the share data. So what is going on here? I want to draw your attention to the fact that, well, if you kind of think about kind of the, well, value and nudgeability distribution among the two types, you see that, well, the low-income consumers, they have a lower baseline inclination to share data, meaning that, well, their baseline privacy valuation is low. However, they are also more easily nudged by choice architecture. So the key mechanism here is that if you have the type of kind of preference structure where the privacy valuation and the nudgeability of the consumers are negatively correlated, that will create a tension between volume maximizing and bias minimizing in the choice architecture design. Okay, so we are going to try to test kind of this theory in the data. Again, we have an experiment. So we are going to have different choice architecture combinations in the experiment. We are going to randomize the default. We are going to randomize the price anchor. And then we are going to elicit the incentive compatible valuation for data for sharing the Facebook data with advertisers using a multiple price list procedure. So this is something kind of you saw in Avinash Kohler's kind of presentation. We're going to use something very similar. And then that allows us to back out a supply curve for every choice architecture condition in our experiment. Now, what that allows us to do is that then we can characterize in different choice architecture combinations and different price points what is the volume of the data shared, what is the composition of the data shared, and that allows us to characterize the kind of volume bias trade-off in different kind of across the choice architecture design. So all of our choice architecture is going to be kind of situated in the context of the multiple price list. This is the opt-out condition, meaning that the consumers will need to make a conscious effort to opt out from sharing. This is the opt-in, and this is the active choice. We are also going to change kind of what we call the anchor price. That would mean the listed prices within the multiple price list. So the caveat here, well, the choice architecture may not look exactly the same as how you would deploy your choice architecture in your website, but this is more of, well, a proof of concept and showed you that, well, kind of in our context, different combinations, there is one that maximizes volume, and we are going to show you kind of the volume bias trade-off in the design. You can think about kind of the framework very similarly in your own design as well. Okay, so what we see here, a few different findings. One, we do see a negative correlation between consumers' privacy valuations in the x-axis and their nudgeability, which is represented in the y-axis. In particular, we see that people who are lower income, who are younger, who are less educated, they tend to value privacy less at baseline, but they are also more easily kind of nudged by choice architecture. So if you kind of deploy a volume maximizing choice architecture, they get to kind of nudge to kind of share their data even more compared to kind of the consumers on the other end of the spectrum. And then we do see that, well, actually, kind of the volume maximizing design can exacerbate the bias. If you look at kind of the two different colors, they represent kind of different kind of choice architectures. The darker ones are the volume maximizing ones, and you see that, well, kind of if you compare kind of the mean income estimate in the sample data the further, kind of the ones that are further away are actually the ones that are more biased. So you see the volume maximizing actually kind of creates a kind of, they are more likely to exacerbate the bias. And this is more likely to happen when kind of, the companies have a fixed sample size budget. And the last thing here in this study is that, well, you see that, well, kind of you can also compare the volume maximizing design with an alternative, which is a bias minimizing design, which is what we are showing here. And what we see is that, well, kind of the gap in between the two designs tends to be larger when the incentive for kind of that you offer to the consumers to buy the data is lower. In other words, if the companies are not offering good value propositions for sharing the data, you see a larger gap in between kind of bias minimizing and volume maximizing, which means that, well, the bias volume trade-off for you is larger. On the other end, if you are willing to increase the price for data, then eventually kind of the volume maximizing and the bias minimizing firms will actually converge, which we think is interesting. Okay, so I think I'm kind of running a bit out of time. How much time do I have? 0. Okay. Okay, that's unfortunate. But I do want to highlight the last bit. Maybe I can borrow 1 minute. So the last study, which we are we are working on with Andre Fracking in the room and Chiara from NATO. We are looking at a different aspect of choice architecture, which is how choice architecture affects websites' competition for consumer data. So for this one, so I'm just going to talk about kind of, the research question. We want to understand, well, kind of usually we talk about kind of the data economy. We think of, well, kind of the data economy as something that has a data-enabled incumbent advantage, meaning that initially your product might just be a tiny bit better. And then kind of rich get richer because you get more data. People are more likely to share the data with you. And then kind of, that allows your product to be even better. So there's a sense of like data-enabled advantage. We want to see whether the presence of choice architecture actually alleviates or exacerbates this type of advantage. And something that we do slightly different here compared to the previous studies is that, well, we want to be able to randomize the choice architecture across big and small websites and across many websites. We can't actually do that by collaborating with a lot of the companies. So what we did is that we use a browser extension to randomize the choice architecture across different kind of websites and see kind of how the effects are different for kind of like across different websites. So punchline. So I'm going to kind of like skip over all of this. Punchline is that, well, we actually don't see any kind of effect of like choice architecture kind of exacerbating the incumbent advantage. So baseline, you see that consumers are more willing to share data with websites that they trust, meaning kind of familiar and popular websites. But the presence of choice architecture does not actually increase that inclination. Okay. So thanks a lot for the attention. Happy to talk about more of this at the Q&A, and I'm going to give the floor to David.
Thanks a lot, and we'll definitely follow up on some more of this. So next up, and our last speaker for the event is David Choi from CMU, and I'll just say that he's going to be talking about this area that I know he's been working on for a while, and that I've been following really closely, and I think I'm sort of most excited about this kind of latest development in this area. So take it away, Dave.
Thanks so much. Thank you so much. And is there a remote control here? This thing. OK, cool. Red button. So I'd like to thank the organizers for inviting me and also for running this amazing and vibrant conference. OK. Bigger one. Thank you. So this talk is on causal inference in randomized experiments where the units are affecting each other through interference, such as peer influence and things like that. And so the formal definition is that each unit's outcome will depend on the treatments of all n other units. So it's a function of, it's an n-dimensional function. The response functions will be arbitrary and unknown, so you might not just depend on your closest friends, but on global effects as well. This includes things like epidemics, peer influence, and stuff like that. So we're considering randomized experiments, and we're restricting just to binary valued outcomes. And this is going to be used in an important way, but I think it can be extended at some point to continuous outcomes as well. It'll look really different, though. So we're not going to estimate treatment effects, which is different from most of the other works in this area. We're going to just try to characterize the interference, try to characterize its prevalence. And so we're going to come up with lower bounds just on the number of units who are affected by the treatment in certain ways, such as who are affected by the treatment, by any treatment, which could be your own or the treatment of others, or who are affected by the treatment of others, that would be spillovers, or maybe by the treatment of others when your direct treatment satisfies some condition, such, for example, in a vaccine study, you might be affected by the vaccination status of others, but only when you get the placebo, for example. Or by the treatment of others, but only the others who are long-range, non-neighboring units. And so our main contribution is to come up with a method that doesn't require assumptions on interference. So we don't assume that you know the true social model or that you're only affected by your closest friends or things like that. And so our estimates will be more robust than those that make these assumptions. And so it's not a treatment effect. It doesn't replace estimation of the treatment effect. We're thinking of this maybe as something which supplements that so that you can also characterize the system that you're studying just by saying there's a lot of interference in the system or maybe there's not a lot. And so since I described many estimands, I'm going to just start with the basic one, and then I'll talk about how it generalizes to the others. And so so the basic estimand will just be the number of units who are affected by any treatment, their own or the treatment of others. And so to set it up, I'm going to define this unknown parameter. This unknown parameter will be an indicator. It will be 1 if you're not affected by treatment, and then a 0 otherwise. And so if you're not affected by any treatments, your outcome is a constant, is effectively deterministic. So it'll be phi star will be 1 in that case. Capital phi will be the number of such units, and so the complement, n minus that, will be the number of units who are affected by the treatment. And that's the thing we're going to actually try to estimate. And so to estimate it, we'll first consider these two estimators for capital phi, the number of units who are not affected by treatment. And so these are kind of unusual. They're inverse propensity weighted estimators, but the event that you're conditioning on or that you're using as the indicator is that your treatment equals the outcome or that your treatment doesn't equal the outcome. And these are pretty unusual. I'll show a picture in a few slides to give intuition on why it's a useful thing to use. And so these IPW weights, they are known. You might wonder, how do we get them since we don't know the outcome model? But since we only need them for the units whose outcome is not affected by treatment, it's effectively just a constant for those units. And so the probability only depends on your experiment design. Because of this, these estimators, they're going to be very well behaved because they only deal with the units whose outcomes are deterministic. And so, for example, if your treatments are independent, then these are just sums of these independent indicators, regardless of interference, because we don't consider the units who are affected by the treatment of others. And so we can't actually evaluate these because they require knowledge of the true phi star. And so instead, we're going to generalize the notation a little bit, and we'll say if there's a lowercase phi as an argument, that'll be under the hypothesis that the true phi star is equal to it. So if you're willing to hypothesize these are the people who are unaffected by treatment, now let's come up with an estimate of capital phi. And so we will use that to our advantage. So in order to get a lower bound on this thing that we want, the number of units who are affected by any treatment, we can take the maximum of all possible hypotheses of these estimators. And so this is just going to be, so we want n minus phi. We're going to plug in an estimate for phi. That'll be phi hat or phi hat 1 or phi hat 2. We'll take the minimum of these two. Since we don't know them, we'll maximize that over all possible values of this unknown hypothesis. And that'll give us something which is extra large for this, which makes this a lower bound from the true quantity. And so if your phi hats are consistent, then the minimum is also consistent. The maximum will be an upper bound on it. And so that's how consistency works. And then the intuition for why we chose this kind of funny looking estimator is that it's going to turn out to be large when the difference in average outcomes between treated and control is large. So if you have a big difference means, you'll be able to say that a lot of people are being affected by treatment. And so the intuition for that is just this little picture. Here we say that the control units have much worse outcome, much higher outcomes than treated. So maybe this is the outcome is a disease and treatment is is a cure, maybe. And so here you can see that the number of units for which treatment equals the outcome is very small. You have a couple people control who don't have the outcome. You have a couple people who are treated who do have the outcome. As a result, you can see that this sum is going to be small no matter what capital phi is, just because there aren't a lot of people for which x equals y. And so as a result, this estimator will be small, and if this estimator will be small, then your estimate will be large. And so if you have a difference in outcomes that looks like this, you can say that a lot of people are being affected by the treatment, just mechanically in that way. And so that's the way this estimator works. And so under reasonable designs, this is going to be a consistent lower bound by the logic that I told you I guess about a minute ago. And then also by that picture, it turns out that this estimator, it'll converge asymptotically to the IPW difference in means. So it's not exactly equal to it, but it becomes vanishing asymptotically close to it. And so this is another way of saying that the diff in means is going to be a consistent lower bound for the number of units who are affected by treatment. I think that's a very intuitive statement to make. So in order to get a confidence interval for this, we're going to have to come up with a variance estimate first, and then we can use asymptotic normality. And so it turns out that the variance of this estimator, it has a form that doesn't show up in other estimators, because it has, we can take advantage of the fact that y is deterministic for the units who are not affected by treatment. And so it turns out phi hat is a, well, let's see. Phi hat is a sum of these covariance of these indicators. And so the variance will just be a sum of these covariance terms of the indicators. And since y is deterministic for all the indicators we care about, this covariance term actually is just known from the design of the experiment. And so in some sense, we can actually, if you knew phi star, you would actually know the variance of the estimator. And so we are not going to actually use this. We are going to take a sample of these covariance terms. And so we're again going to just sample the ones for which both units treatment equals the outcome, and then importance weight appropriately. It turns out when you do this by the same logic as before, if the difference in means is large, only a few units will satisfy this condition. And so only a small number of covariance terms will enter this variance estimator. And as a result, even if you maximize this variance estimator over all possible hypotheses for the unknown phi, it'll stay small, just because there aren't a lot of terms that satisfy this indicator function. And so as a result, our confidence intervals are going to be tighter as well that way. And so maybe I should have shown this slide first. Under reasonable designs, these estimators will be consistent and asymptotically normal, which means that they're both going to give you one-sided intervals for this quantity of interest here, where these are just the variance estimators. And so we don't know for the phi star, so we can't use these. Instead, we'll do the same trick as before. We'll say we have these two intervals, and then we can take the smaller of the two, the tighter of the two, but we'll maximize over this unknown phi parameter that says who is unaffected by treatment. And then if we maximize over it, that gives us a conservative boundary for the true one-sided interval. And so it'll also have coverage at the desired rate. And so we can. So that's the basic approach. We can now add some bells and whistles to it. And so the first thing I'm going to do is I'm going to incorporate network information. I will say, suppose we have a network, and suppose we have this indicator for the number of treated neighbors for each unit, where you have to choose the threshold. And so if you wanted to, you can incorporate that into this approach. You could say, well, instead of looking at the event x equals y, you could say your treatment equals your indirect treatment, which also equals your outcome. And so this would be looking at people who are treated, have a lot of treated neighbors, and have the outcome, or they're control, they don't have a lot of treated neighbors, and they don't have the outcome. And so it turns out that will also, by the same arguments as before, this will also give you a lower bound on the number of units affected by treatment of others, but it will converge to a different contrast. So this contrast compares people who are treated with a lot of treated neighbors, people who are controlled without a lot of treated neighbors. So, and so this, if there are indirect effects and they sort of are in the same direction as their direct effect, then this might be a larger contrast than just looking at direct effect alone. So in that case, this would give you a tighter lower bound on the number of units who are affected by the treatment of others, which again, I think it is intuitive that this would be the case here. Okay, and then the next wrinkle I'm going to add to this is that to reduce variance, you have these IPW estimators, and then you could Hayek normalize them. And so the way I wrote the formula is concise, but a little not the most transparent way to do it. I think if you look at the write-up, you can see a little bit more of the derivation. But suffice to say, you can take these IPW weights and then you can normalize them by the sum of the IPW weights for people in the same treatment condition. And it turns out that will reduce variance just as it does for ordinary treatment effects. And then the same arguments for interval construction and point estimation will carry over. So I should also mention something about computation. So in order to construct these intervals, I'm having to solve these optimization problems where I'm looking for the worst case bound over all values of this unknown parameter, which is a binary, n-dimensional binary vector, identifying who is affected by treatment, who is not. And so that it boils down to estimating this this kind of conic function here. So beta is your unknown thing, and then it turns out this here becomes your point estimate. This here's your variance estimate here, and then so it's not trivial to solve this thing. In general, in the worst case, this will be hard to solve. But in practice, branch and bound seems to work pretty well, provided that you formulate this in the right way. And so we don't solve it just like this. We rewrite this quadratic term using some tricks that are pretty standard, I think, to convert it to a linear expression. And then at that point, in practice, it seems to work pretty well for moderate sizes. So that's the general approach. We first say that there's this unknown parameter saying who is affected, who is not. If you knew it, of course, you could come up with these great estimators, and then we bound how large the estimator could be over all values of that unknown parameter. And so you could generalize that approach to the various other estimates I talked about, like the number of units affected by the treatment of others, affected by the treatment of others when you're treated yourself or when you're not treated yourself, or the number of units affected by not just any others, but others who are sufficiently far away. They each follow similar steps as before. I'll show just the next one on the list, and then I'll give a general template. I'm just showing this to show that the ideas are pretty similar here. So we're again going to have this introduce this parameter. It says who is affected by the treatment of others, who is not. So one, if your outcome only depends on your own treatment. So you're not affected by treatment of others, 0 otherwise. And then so this would be the total number of units who are only affected by your own treatment. And minus that is the thing you actually want, the number of units who are affected by the treatment of others. This will be the thing we estimate, we plug in to get an estimate of theta. And so the idea is pretty similar. We again can come up with IPW estimators saying if you knew this unknown vector, then you could come up with a nice IPW estimator for this. We don't know it, but we can maximize over all possible values of it. And then we chose these two, and then we take the minimum. And it turns out if you choose this particular form, the point estimate converges to the difference in means. And so this is a slightly different difference in means. Here we have to condition on your direct treatment in order to get this to be a consistent estimator of the thing we're trying to get here. So that's a little bit different from other estimates of treatment effects you may have seen. And then, of course, we have the coverage of our constructed intervals as well. So I mentioned many other cases as well, and they all follow this general template where you say that we come up with this unknown parameter, which is 1, if your outcome satisfies some exposure model for all x that are in some region here. And so those exposure mappings and these sets are specified by the researcher to define what the estimate is that you're interested in. And then once you define that, that gives you these IPW estimators for the complement of the thing you're trying to estimate. And they take this form here where you're saying, 1, if you're in that condition and your indirect treatment equals the outcome or doesn't equal the outcome for the other one. And then you have to divide by the inverse propensity weight, but you condition on this thing that appears in your exposure model here. And then once you have that, then the results carry over. This thing here, the minimum of the two maximized over the unknown parameter, it converges to a lower bound on the thing you want, and also to an IPW contrast here as well. And then Hayek normalization also works as well. So I'm going too quickly, but I now will show some simulations and data examples. So in my simulations, I'm going to compare, just to compare the interval widths and the coverage rates to treatment effect estimation. I'm going to compare to this particular type, which is known as the expected average treatment effect. And so this is an assumption lean kind of treatment effect that people have been studying for some time. You can think of it as your expected outcome if you're treated minus your expected outcome if you're control. And so this is sort of like saying under the experiment design, is it better to receive treatment or control? So changing one person at the intensive margin here. This expectation is over the randomization of the current design, so it only applies under the design that you're currently experimenting with. And so you can generalize this to other exposure conditions, like your outcome if your neighbors are treated versus your outcome if your neighbors are not treated, and other things like that, which makes it you can, for every estimand you're looking at, every estimand we're looking at, there's like a corresponding EATE that we can compare to. And so to get intervals for this, I think this was a plenary talk at last year's code conference. So Gao and Ding studied Hayek normalization estimation for this estimand. And so for this, they propose a conservative sandwich variance estimator, which is a little different from the naive one, in that you have to take the projection of this dependency graph, and then that adds a little bit extra conservativeness that you actually need when the treatments have a network design in them. And so for stability of this variance estimate, you need to assume bounds on interference so that the dependency graph of treatment and others and outcomes is sparse. So you need to make an assumption saying that your outcome only depends on a certain subset of the other units in the experiment. Okay, so in our simulations, so we simulated this model where your outcome depends on your treatment and then on your treated neighbors here in this kind of simple linear fashion. This is a pretty nice case. Like this, we're assuming that our indirect treatment indicator is the one that's actually being used in the model. So this is somewhat of a best case scenario. So for this nice case, our approach is able to give calibrated cover intervals for some of these estimands, for the number of units who are affected by any treatment, or for if you're affected by a treatment of others, if you're treated yourself, or if you're control yourself. For these, we have calibrated coverage and unbiased point estimates here. For the others, we're conservative, as our results would suggest here. Also, our widths are often competitive or even smaller than those of the treatment effect. I think one way of thinking about this is that we're estimating something easier. We're just estimating the number of units who are affected by treatment and not the direction or the sign. And so it kind of makes sense that maybe there are some gains, maybe it is easier to estimate in some way. I think what happens is that we're able to have a variance estimator that's less conservative than the one that's currently known for the treatment effect. And so I think these results are promising and suggest that this approach may be of use in practice. So we also looked at a data example. So this is a paper published by Kai et al. In 2015, where they ran an experiment, and they took rural farmers and randomly assigned them to information sessions where they would receive high or low amounts of information about a crop insurance product, and then they were asked to make a purchase decision on it. And so some of these sessions occurred before others. And so if you were in the later session and your friends were in the earlier session, there was a chance for some sharing of information to happen informally between you and your friends. And so they also elicited network information, asking each person to list their friends who they received advice about finances or farming from. And so what they found is that farmers in later sessions had higher take-up when more of their listed friends in earlier sessions received high information, particularly when they themselves received low information. And so if they didn't get a lot of information, but their friends in an earlier session received high information and shared it with them, then maybe that was a mechanism where it caused them to make the purchase more often than if they hadn't received the information. And so the results are that we estimated this theta control, so it's whether you're affected by the treatment of others, provided that you received low information. And so the point estimate is that 23% of the farmers in the second round, if assigned to low information, they would be affected by information given to the first round. The one-sided interval for this is at least 9%. That requires no assumptions except just the known randomization design of the experiment. To estimate a treatment effect, you might consider this one. This would be like maybe the corresponding version, where we compare if you receive low information, but your first round friends receive high information, versus you have low information and your first round friends also receive low information. And so for this estimate here, it's the same point estimate, it's the same difference in means. Their interval is wider, and it also, they need to assume no interference between villages for this to hold. And so that, in assumption, it may be questionable. There are cross-village friendships that were listed in the data. But you could also make a case that maybe I think you could make the argument either way. It's not fully. I think it would be debatable in both directions. So the goal of this paper was not to say that this is some kind of mechanism where we should necessarily split people in different units and then encourage this to get more higher take-up or things like that. The goal was just to study social influence in this controlled setting, and then just to demonstrate that people do talk to each other, and the things that they share with each other could be important. So for that purpose, I think it might be acceptable just to give the prevalence, to give the estimate we're returning, to say there are a lot of people who would be affected by the information given to the first round. And so this parameter is easier to estimate. It has tighter and less questionable CIs, and so I think it could make a good complement to estimations of treatment effects as well. So that wraps up my talk. We estimate the number of units who are affected by treatments in various ways. It doesn't require any modeling assumptions on interference. It only requires the known design. And so I think I have a previous attempt where I did something which was actually more complicated but worked less well. And so I think this is an improvement on the previous attempts. It gives things that are much tighter, much less conservative. I think at this point it may be previous works were maybe more of a proof of concept, and maybe this could actually be practical for certain settings, I think. Thank you.
Very interesting. So actually, if both of you can just join us again, then we can discuss both of these talks some more. I just wanted to follow up with one point, which I think maybe will lead into some connections here, which is that you frame this in terms of the number of units affected by treatment. If we were to assume monotonic treatment effects, we can get a bit more. Could you say a little bit about that?
Yeah. So then it wouldn't be conservative. I think it would be tight. I don't know for sure, but I bet you can squeeze out tighter variance bounds somehow as well from that as well. That's my thoughts.
And so just kind of thinking about that and how reasonable this kind of monotonic treatment effect assumption is, it made me think a little bit about some of these effects of different choice architectures on different types of people. And I wonder whether, Tesary, you've looked at cases where actually there's a choice architecture backfires for some people and is working for others, or whether these effects are sort of weakly monotonic still, but it's just that they're really working for some groups rather than others.
Yeah, so in the second study that I mentioned, we look at the effect of the price anchoring, and we see that it actually has kind of non-monotonic effects, because something that we did in our particular valuation elicitation, we allow people to say that I don't want you to share the data for any price. And somehow what you see is that if you put people in the low price anchor condition, which would kind of nudge people into sharing data more aggressively, some of the people who report limited valuations, they change their valuation downwards, but it also increases the proportion of the people who say, I don't want to share the data at any price. So that is a very concrete example of backfire, that you mentioned.
Yeah, and this kind of splitting effect where people anchor, I guess psychologically, people are anchoring on this price. Some people are saying, oh yeah, I'll think about that price as a reasonable price. Other people are like, no way, I'm not that cheap. In fact, I'm really not that cheap. I'm choosing never, right? Is kind of what you might imagine as some of how that anchor is functioning psychologically. Right,
so we are not directly testing any psychological mechanisms, but you could imagine kind of people are using that as a kind of, a information updating device. Then if the price anchor is in a reasonable range, then I would say, okay, so I'm going to update my prior accordingly by summing up the price anchor and my prior. So in that case, that would be effective. But if the price anchor gets too low, then they're going to abandon that. They may even get upset about it, and they're more likely to say no. And I think you see this not only in the anchor in our study, in other settings. I've seen previous studies that focus on the default effect. Sometimes you also see backfiring effect from setting a very aggressive default as well.
Mm-hmm. That I think was a much more sophisticated account of how that worked. And I can see the connection with decoy type effects, where if you're moving some other product that at some point it stops being relevant. Cool. So I think we can take any questions from the audience. I don't know if we have people moving the mics. Looks like the mics are now standing here. So if people want to ask a question, feel free to step up to the mic that are just on these stands. Whichever one you want. Yeah. That's the decoy. Oh.
So I think this is more for David than I was just, maybe I missed part of misunderstood some part of your talk. And I think it's related to a question which was asked earlier. How does this work for subgroups in your data, right? So you might have, you were how many people were affected, might have been affected, but if I ask how many people of, certain group, of a certain age, of a certain race, whatever, are getting affected.
Right.
Do you have any thoughts on that, or? Yes, I don't know.
I haven't thought seriously about that. I wonder if my thoughts are it should be doable, and then it's just a question of whether it is tricky or not to do. But I believe you should be able to break these down by those effects as well, by those groups. May I ask a question to Tesary?
Oh yeah, go for it.
So sometimes I think that for my preferences of privacy, if everyone is sharing the information, somehow I feel like it's okay for me to share also. But if I were the only one, I would feel more scared to do it. I don't know if that is rational, or if I don't know if that's just being irrational, or if that actually makes sense in some sort of it's safer when more people share. Is that something that is considered, or is it?
Yeah, I think you could try to rationalize it from a information theory account, because, so there are actually two different related theories that could explain this intuition, if I may. So I think one type of theory is that, information has externalities. So if your friends already share a lot of information, or even unrelated consumers who look similar to you that already share information, then it will mean that, it's going to be easy for the companies to infer about your preferences and interests. So then the benefits or harms of sharing your particular piece of information would matter less. So from that account, I can see that, if previously you were caring about the privacy harms from an instrumental standpoint, having the other people already sharing could alleviate that concern. So that would be one theory.
And I might say, especially if you thought that whatever your sensitive characteristic or behavior is quite predictable from what you know about these similar people.
Right.
Right? So, it could be different whether, the people who look like me are doing the sensitive thing that I don't want people to know about me, and so it's already inferred from these people who look like me, or whether it's actually still unpredictable given my characteristics, I guess.
Right, exactly. And I think I also want to because another related theory, which actually goes back to a lot of the discussion about differential privacy, is that, it's actually easier to protect people's privacy when there are a lot of people sharing, because to some extent, if it's only you who are sharing the information, the influence function gets larger. So it's when you extract your data out, the estimate changes more. Versus if there are already a lot of people sharing, it doesn't, extracting your data out versus in doesn't change the estimate that much. So it might be another way to reframe the information externality, but it's it's actually saying that, when there are already a lot of people sharing, the impact to your privacy personally is going to be dampened.
Thank you.
And we could certainly imagine then wanting to try to detect these sort of interference effects in cases of studying privacy choices, right?
Yeah.
I don't know if you've seen anyone try to do that sort of thing. Obviously not yet with Dave's fresh methods, but in general, it seems like a natural a natural question, and I guess we would imagine sort of peer influence in everything, including that.
Yeah. I have not seen particular kind of studies on that, but I think it's definitely a fruitful area. Yeah.
Oh, cool. And we've got David
yeah.
lining up.
I guess a question for David. So I noticed in your talk you were like, yeah, this works for pretty good sample sizes, like n equals 1,000 or so. And obviously we have a lot of people in this room that run experiments that are orders of magnitude bigger. And so I guess I was wondering if you could say anything about, are there ways to get slightly worse bounds or something, but to maybe get solutions that are adjacent to what you're proposing, but a little bit more scalable?
That's true. I forgot the room I was talking to when I said that 1,000 is pretty good. So the point estimates are going to be fine. The point estimates don't require any computation, so those are fine. I think if you have, if the design is such that you have clusters, and so like, if the people are sort of symmetric within the clusters, not in their outcome, but just in the design, like you're willing to say, we have villages, and then we're going to treat each village as a clique for the purposes of computing W and I guess W basically. In that case, you can then do much larger problems because you don't really have to do a binary variable for every person. You could just have a variable for the number of people in that village who have the indicator or not. And then it scales up pretty well then.
And did you have to do that kind of thing in the Jing Tsai et al. Example? Or
Not
because,
for that.
okay.
I did it for this worms paper that was, I guess it's about 1,900 people in that one.
So one question about privacy that I think particularly when we're trying to quantify the value of data for someone or how much they're willing to share, personally, it's extremely hard to me to know what the value of my data is, right? Like, is it $10? Is it $50? Have you thought or tried about like monetizing it differently? Like, what is, I don't know, the social influence I would lose, or you'd lose this discount because your ad is not personalized, so you'd lose this item that's highly personalized to you. It's like, are there other ways of quantifying the value of sharing your data that's more that's less monetary, because currently it doesn't provide money value as much as it provides other value that's, I think, less tangible and more nebulous?
Right, that's a good question. So I guess if I may reframe your question a bit, is that, well, kind of how should we think about the value of data if you compensate the consumers not using money, but using kind of, some other types of like basically benefits and harms?
Which is really the value that we get when we share the data. We don't necessarily get money as much as
Right. So there is a very cool study from JMR, so Journal of Consumer Research, that shows that, well, you could, so they basically compare kind of the valuation if you kind of, compensate the consumers using implicit kind of means, meaning kind of services and kind of products. And what they show is that if you kind of try to use the implicit prices rather than the explicit prices, consumers willing to accept tend to be lower. Now, I think it's a bit tricky to think about kind of, the value of kind of services and products, because, kind of if you start to introduce that, then the question is, how much value do consumers place to kind of, say kind of, social harms and things like that? Then you would want to kind of add another kind of, layer on top. And I'm an economist by training, and kind of, usually we think about kind of quantifying everything kind of using dollar terms. And that also seems to be kind of what the policymakers are thinking about when I talk to FTC. So I'm a bit biased kind of, like towards the kind of, the dollar value measure, but I'm totally with you. There are a lot of the time kind of companies using the implicit instead of explicit. You could even say, it's kind of a strategic decision on their end, because, it does seem that, consumers kind of value their data less when they're compensated in implicit means.
And I guess to relate that to something else you talked about, it seems like that other sort of compensation might function differently in terms of the selection bias or sort of who that convinces to produce data, rather than, with monetary incentives, we'd really expect it to often have this character that high income people are not nudged much by a higher offer.
That is totally plausible. I do not have direct studies that directly look at this, but I think I completely buy the argument that, if you start using kind of implicit methods, then you are kind of less likely to screen out the high income people. I think you may actually kind of be able to draw evidence from kind of all the survey kind of research methods, because I think what they have been showing is that, well, you could kind of incentivize people to kind of participate in the survey using money, or kind of appeal to kind of social norms, or kind of kind of reputation, and usually you get less of kind of selection by income when you use, say, kind of social norms, etc.
Yeah, great. Oh, we have another question over here.
I have a question for David. So your research is on network. So how do you solve the problem of endogeneity of networks? Because my background is economics, and there are a bunch of economics literature talking about endogeneity. For example, my friend influenced me, and my outcome also influenced my friend. And second, when we choose the friendship, also we have some counterfactor that cannot be controlled. So how can you solve the endogeneity when you do the estimation?
So I guess we do some bounding. And so because of the bounding, if we don't have the right network, if it's just a crude proxy, we might lose power, but we won't lose validity. We won't lose coverage of the intervals. The network does need to be elicited from pre-treatment covariates, though. And so again, that could result in not being able to use post-treatment ones could result in loss of power, because you don't have the true network, and so your contrast based on that indirect treatment variable might be really weak, because you're not really comparing the people who you should be comparing to.
Okay, thank you.
Yeah, and I guess a natural question there, what might be, is there some way you could extend your framework to use sort of an endogenous or changing network that might be responding to treatment? I think this is something that came up a lot today.
That's a good question. The most I would be willing to make a gamble on right now would be to say, maybe if you could train a predictive model on some of the data, you could maybe, but that's kind of just trying to get at what you're doing, but really not going at it head on. I'm not sure if I could do it.
Yeah, or it's sort of just doing some dimension reduction that's guided by network evolution would be maybe what that is, right? As opposed to actually using the changing network itself or something, yeah.
Yeah, that would be very interesting. Yeah.
Cool. Malika?
Yeah, I had a question to Tesary. I really like your research on consumer privacy evaluations, and I'm curious, how do you think the choice architecture of the websites will change as a result of differential privacy? Do you think consumers would be more willing to share their data, and what kind of consumers would be most impacted?
So, okay, are you asking about the choice architecture evolution after differential privacy?
Yes.
That's an interesting question. So I've been thinking about the interaction between choice architecture and kind of differential privacy, and maybe kind of privacy technology in general, but in the other direction. So because, well, this is in the context of the sandbox, and kind of my colleague Garrett Johnson has been working on that. And something that came out, I'm pretty sure kind of many people in the room are aware, is that, well, kind of Google basically says we are not going to enforce kind of sandbox anymore, but we are going to give consumers the option of kind of opt-in versus out, kind of the third-party kind of cookies, while kind of keeping the sandbox there as an option. So I've been thinking about kind of the how the choice architecture is kind of presented for the third-party cookie consent is going to affect a lot on kind of the privacy tech adoption. So I've thought a lot about that domain, but kind of the reverse, I've not actually kind of thought a lot about that. I think that's a good question.
Okay, so I know there's a lot more we could talk about. We're actually right at the end of this plenary session and getting to the end of the 11th annual code as well. So I just want to go ahead and thank both of our plenary speakers. I also just want to say a little bit more to wrap up the conference. And so first I want to thank again our sponsors this year, who have some of whom have been involved in code for several years now, and some of whom are new. And so we have our premier sponsor, Netflix, coming back They were the premier sponsor last year as well. Our event sponsors, Amazon, Booking, and StatSig. And StatSig newly added as a sponsor this year, and the other two were sponsors last year as well. And then our reception sponsor, and we're about to go to the reception, so that's nice. EPO returning again as a sponsor this year. So we really appreciate that support. Now you're going to have a chance to check out any posters that you missed out on the previous day. And I also want to just thank the broader support team and event team that we've had for this. So we've had the AV team that's been making sure that this all works well together. So thanks a lot to the AV teams. And in particular, one of the things that I've been reminded of recently when I've gone to some other conferences organized by other faculty is just how amazing our non-faculty team is at the Initiative on the Digital Economy. And so they make putting on this conference really a pleasure for the faculty who are organizing it. And so and in particular, the team, really involves everyone from the IDE, but in particular, Carrie Reynolds and Eileen Manuas are like really putting together a lot of this event. And if you like this event, there's actually another event put on by the Initiative on the Digital Economy with a bit of a different focus coming up on November 15th. It's Big AI, the business implications of generative AI. It's going to be a bit more of a tilt towards people interested in kind of strategy, high-level implications of that, a little bit fewer equations probably on the slides, but I think it's going to be a really stimulating event. So, and I think there's still some room for registration. So I want to thank my fellow organizers, the Technical Program Committee, and all of you who've participated either as asking questions or presenting in any number of the parallel sessions or the poster session. So thanks for the great code, and let's check out some posters.